Hello calculus students. In this video I am going to show you why this particular series converges. And again, for all of these series it's never truly intuitive why. We could list out a few of these terms. So the first term would be 1/2, because you're plugging 1 in here. The second term would be 1/5. The term after that would be 1/10, and so on. So 3 squared plus 1 over that is 1/10, and so on. And we need to show how this series will converge, or at least we need to show that it converges. We don't necessarily know what it converges to. Okay. So we're going to use the same idea as we did in the last video, where we compare this to an integral with just some slightly different wrinkles here. Okay, so let's look at the graph of f of x equals 1 over x squared plus 1. So at 0, we actually get 1. Okay. And it actually goes up a little bit. Oh, actually, no, it doesn't go up. It curves a little bit, and then it levels off. Okay. Just like so. Alrighty, and then so this is the function f of x equals 1 over x squared plus 1. Then we can look at these little rectangles, starting at 1, 2, 3, 4, 5, and so on. And this time, the way that I'm going to draw this rectangle is I'm going to start there and going to the left this time. Okay, so this is RAM, or right rectangle approximation method. Okay. So I have a bunch of blue rectangles. Okay. And we can just look at this area here. I shouldn't have done that. Let's look at this, the red area first. Okay, the red area here. So the red region is equal to the integral from 1 to infinity of 1 over x squared plus 1 dx. Right. And the blue region here like so, is equal to this series, however, starting at 2 instead of starting at 1. So the area of this rectangle has a base of 1 and a height of, this height here is f of 2. Okay? This height here is f of 3. All right. So we actually miss out on one part of the series here. So this is the blue region is equal to the series n equals 2 to infinity of 1 over n squared plus 1. Okay. So this is not exactly the same as the series that we had before. Okay. But we can. This is still enough for me to show you that it is convergent. Okay. So now it is clear from this picture, at least, that the blue region is less than the red region. And again, the blue region is not the same thing as the series that we're working with. It's almost the same thing. It's the exact same series with one missing term. Okay? But we're going to show that the blue region is clearly smaller than the red region. So the blue region is definitely less than the red. Okay. So that means this series, n equals 2 to infinity of 1 over n squared plus 1, must be less than the integral from 1 to infinity of 1 over x squared plus 1 dx. Okay. And then we're going to evaluate this integral. So this is less than the limit as b approaches infinity, evaluated this integral from 1 to b of 1 over x squared plus 1 dx. And the antiderivative of this expression, of the integrand here, is simply the arctangent function, or the tangent inverse function. So this is the tangent inverse of b minus the tangent inverse of 1, okay, which turns out to be, now first, the tangent inverse of 1 is just pi over 4. And, well, wait a minute. That doesn't sound, oh yeah, it is. That's right. Okay. So the tangent, this is the limit as b approaches infinity of the tangent inverse of b. And this is pi over 4. Okay. Sorry, it's early in the morning and my brain's not fully functional yet. That's pi over 4. Now the tangent inverse function, this goes back a while, but the tangent inverse function actually looks something like this. Okay. It has two asymptotes, two horizontal asymptotes. Okay. Leveling off here at pi over 2 and down here at negative pi over 2. Okay. So the tangent inverse, as x approaches infinity, the tan inverse function actually approaches pi over 2. So that means this limit here is pi over 2. This limit right here is just equal to pi over 2 minus pi over 4, which is equal to pi over 4. Okay. So the blue, so let's get back to this, right? So the blue region, or this particular series here, is less than pi over 4. Okay. Now let's use this fact to answer our original question, because we didn't actually answer the question that we were asked to answer yet. Okay. So all we really know so far is that this slightly smaller series, n equals 2 to infinity of 1 over n squared plus 1, is strictly less than pi over 4. Okay. Now let's compare this series here to the original series that we were asked to deal with from the very beginning. Okay. So this series here that we use to compare to the integral is the exact same thing as this series plus one additional term. So let's just make a quick note. The series from n equals 1 to infinity is simply equal to the series from n equals 2 to infinity. Okay, and I'll put this in parentheses, plus the first term. Right, because from n equals 1 to n equals 2, all you're really doing is chopping off the first term. So, and the first term of this happens to be 1/2. Okay, so that means that the original series starting at n equals 1 is strictly less than pi over 4 plus 1. No, I'm sorry, plus a half. Okay. So there you have it. We've shown that this series must converge. Now, very important note here to point out, all we've really shown here is that it must converge to something less than pi over 4 plus a half. We don't actually know the exact answer. We don't really know the precise simplest radical form or the exact representation of what it is. All we really know here is that it converges. converges. And if you look at the original question, it's posed very carefully. All it says is that show that the following series converges. It doesn't say anything about finding what it converges to or finding the limit of all the partial sums. It just says figure it out and show that it converges. Okay. So these past two problems illustrate a nice technique in mathematics in dealing with series. Is that if you have a series and you want to show that it is divergent, then you look at that integral, or you look at that function and look at the integral, and show that the series is larger than the integral, and that the series diverges. And if you want to show that the series converges, then you just manipulate the series in a way so that it becomes smaller than an integral. And if that integral converges, then the series must also converge. So there you have it, two problems here. You may have a lot of questions and maybe some counter examples that you want to present. That's absolutely the right thing to think about. Ask if you have any questions. Thank you for watching, and have a wonderful day.